Progressions is the topic which we are going to discuss for the session. What is progressions, or how do we define that in mathematical terms, is the biggest question out here. As we have been coming across many situations in real life of patterns. For example, I have a number 3 and then a number 5 and a number 7. Then immediately I can say that based on 3, 5, 7, my next number is 9, 11, 13. So from the first 3 or 4 terms, I can identify the 5th or 6th term, which we can easily identify through a pattern. Therefore, here to start with the topic of progressions, progressions is nothing but a pattern. Anything which follows a pattern comes under progressions. The pattern can be either, for example, if I take 2 squared, 2 cubed, then immediately I can say the next term is 2 power 4, because I can say this because I know that the first 3 terms are following a certain pattern. Therefore, 2 squared, 2 cubed, 2 power 4, 2 power 5, 2 power 6 is how I identify the pattern. So with the minimum information given, if you can identify the extended part of it, is what is called a pattern. Let's try some practice problems in identifying the pattern. Then I would like to know the next term in this pattern. I clearly see that when I add 4 to 1, I get 5. When I add 4 to 5, I get 9. When I add 4 to 9, I get 13. Therefore, when I add 4 to 13, that is 13 plus 4 equal to 17 is the next pattern, followed by 21, 25, etc. So every problem need not be with the same pattern. Different problems come out with different pattern. For example, here all terms are raised to integral powers with respect to integers. Here each of the term is added with 4. So like this, we have different patterns which follow different sequences in identifying whether adding of 4 or raising it to power 2. Let's try some more problems for practice. For example, I have how do I know the next term here? So all patterns are not easy because some patterns are easy to construct, but some patterns are very complex. Say for example, with this example problem, 1, 3, 6, 10, etc. So my first term is 3 and my second term here is 3 and the third term 6 and the fourth term 10. Then what is the fifth term is the biggest question of the problem. So what do we get in the next followed pattern? Identifying the pattern is very important than writing the pattern out here. So what would be the next term out here? What kind of a pattern does it follow is what we're going to see. So let's see here. As I see the first term, this is 1, and as I see with the second term, this is 3, which is 1 plus 2, and as I see with the third term, this is 1 plus 2 plus 3, because each of the integers are added respectively in each of the term. 3 plus 2, 5 plus 1, 6, 2 plus 1, 3, and 1. And finally, my 10 is 1 plus 2 plus 3 plus 4. When added, 4 plus 3, 7, 9, and 10. Therefore, my next term is said to follow the similar pattern with 1 plus 2 plus 3 plus 4 plus 5. So therefore, my next term which has to be found will be 1 plus 2 plus 3 plus 4 plus 5, which gives me 15. So 15 is the next term of the pattern, is how we identify. So there might be various forms in mathematics or the mathematical properties through which patterns exist. It is very important to identify the exact pattern which the mathematical terms follow. In this case being 1, 1 plus 2, 1 plus 2 plus 3, etc. 15, and then comes 21, etc. is how we identify the pattern here. Now let's come to the most important pattern in mathematics called the Fibonacci sequence, which is still a mysterious fact in mathematics. So let's see what the Fibonacci sequence says in its own terms. To start with, 0, 1, 1, 2, 3, 5, etc. So what kind of a pattern is this, and what are the next terms in the pattern is what we are going to identify here. This sequence is called Fibonacci sequence, one of the most important sequence in mathematics, connecting the golden ratio with it. So how do we identify the pattern here? Here it has been 1, 1 plus 2, 1 plus 2 plus 3, etc. And here it has been adding of 4 each time. And here it has been raising of the power 2 each time the sequence proceeds further. Then how do we identify the pattern here is the biggest question for the problem. So in this case, as I see here, when I take the first two terms, when I add the two terms, 0 plus 1 is 1. So when I add the first two terms, it gives me the next term. And when I add these two terms, it gives me the next term. That is, the next term is obtained by adding the previous two successive terms. That is, as I see here, 0 plus 1 is 1, and 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. Therefore, we can guess the next term being 3 plus 5. Therefore, I get this as 3 plus 5, which is 8, is the next term. And then finally, the next term will be 5 plus 8, which is 13, etc. So this kind of a sequence where the next term is the sum of the previous two terms successively is called a Fibonacci sequence. The terms being 0, 1, 1, 2, 3, 5, 8, 13, etc. is called a Fibonacci sequence. So this kind of different types of sequences is what we are going to discuss in this today's session of progressions. The other word for progressions is following of a pattern. So let's see the different problems followed with different patterns out here. Now let's see how the progressions has come into existence with the real life situations. Progressions are generally used in everyday life. Unknowingly, we don't know that we are using the concept of progressions, but we use progressions in daily life very much. The applications of mathematics in daily life. For example, I go to a bank, then most of the banking transactions happen through progressions. As we can see here, for example, I go to the bank where I deposit a sum of 5,000 rupees in the bank. So when I deposit rupees 5,000 in the bank, the bank gives an interest of 200 rupees every year. Say for example, for the amount of 5,000, the bank interest per year is rupees 200. That is, every year uniformly there is 200 rupees which is increased as the interest for the deposited amount of 5,000. So after 6 years, I want to go and collect my money. So if I go after 6 years, what will be the amount of money? How much is the money I collect? Do I collect is the biggest question here. So after 6 years, definitely the money increases because the interest rate is 200 per annum or per year. And after 6 years, how much money do I collect? These are the transactions which we do in everyday life. Every household deposits money in the bank, and we use, interestingly, the progressions or the patterns in case of this real life situational problem. How do we use it is the biggest question for this real life problem. As I see here, I can see that in the first year, my deposit of 5,000 increases with 200 rupees as the interest. Therefore, this comes out to be 5,200. And therefore, my second year will have another 200 added to this, So I get 5,400, then 5,600, 5,800, so on and so forth. Therefore, let's start with second year, where this amount is added with 200 because the bank gives an interest of 200 rupees per annum. So this gives me rupees 5,400. Again, in the third year, 200 is added to this. So I get 5,600, 5,800, 5,000, 6,000. So 1, 2, 3, 4, 5 and 6,200 is the amount which finally collects in the third year, fourth year, fifth year and sixth year. Now in the sixth year, this amount accumulates to rupees 6,200. That means by the end of the sixth year, I'm going to collect an amount of 6,200 years. For the initial amount which I deposited is 5,000 rupees. That means I'm at a profit of 1,200 rupees because the difference is 1,200. I'm at a profit of 1,200 rupees when I deposit the amount in the bank and remove it after 6 years. So this is how we understand the patterns in real life. Why do we know that this is increasing by 200? Because by the first 2-3 terms, we follow there's a pattern where every time it increases by 200, the amount increases by 200, and finally we get a pattern with this. This is an example of a pattern or a progression used in daily life. Now that we have seen various types of patterns in our example cases, we have many patterns in mathematics which have their own respective ways of identifying the different numbers in the patterns. But here, the two important patterns which we're going to discuss in the syllabus are the arithmetic pattern and the geometric pattern. So in progression, there are two types of progressions which we are going to discuss mainly in the session. So the two types are the arithmetic progression and the geometric progression are the two types of progressions which we are going to discuss in the session. So here, as we have identified that a progression is a pattern, therefore an arithmetic progression and geometric progressions are also the different types of patterns with their respective definitions. So let's see each of the progressions in detail with their own definitions. But before that, generally an arithmetic progression is denoted with the abbreviation AP, which stands as arithmetic progression. And then a geometric progression is denoted with GP, which stands for geometric progression. So to start with the arithmetic progression. So what is an arithmetic progression? The first type of progression or the pattern which we're going to study. So what is an arithmetic progression is the biggest question out here. So an arithmetic progression is a pattern in which a fixed number is always added to each of the terms. So therefore, to understand this more clearly, let's take the definition. A pattern which has fixed element added to each of its term is called an arithmetic progression. So what do you understand by a pattern which has fixed element? Now this is a very important role which plays in arithmetic progression. So pattern which has fixed element which added to each of its term. Let's see with an example. For example, I take a pattern 1, 5, 9, 13, etc. This example has already been discussed, where let's again revisit the same example problem. Now if I take the pattern 1, 5, 9, 13, 17, in this case, what is the fixed element which is added? Now as I see here, let me rearrange so that my first term is 1, but my second term is obtained by adding 4 to the previous term, Next, my 9 is obtained by adding 4 to the next previous term, which is this. So this is added here, and this is added to this, and next 9 plus 4 will give me 13, and 13 plus 4 will give me 17, and 17 plus 4 will give me 17, etc. That means, as I see here, this is reduced to this form, where 5 is written as 1 plus 4, 9 is written as 5 plus 4, 13 as 9 plus 4, 17 as 13 plus 4, which makes me understand that every element is obtained by adding 4 to the previous term. 5 plus 4 gives 9, 9 plus 4 gives 13, 13 plus 4 gives 17, 17 plus 4 gives 21, 21 plus 4 gives 25, is how we get. Here, this strictly follows the definition that this is a pattern which has fixed element, which is 4, added to each of its term. Now in case of this example problem, I see that the fixed element 4 is added to each of the term of the given progression or a pattern. Therefore, this kind of sequence where a fixed element is added to each of the terms is called an arithmetic progression, as given by the definition. The fixed element here is 4, is what we identify in an arithmetic progression, this being one of the example. Let me take one more example. Is this an arithmetic progression? Is the question out here. Yes, it is, because every element is obtained by adding the fixed element 0 to the previous term. Therefore, here the fixed element is 0, which gives me 7 plus 0 as 7. So, because I can add the fixed element 0, I say this is an arithmetic progression, and this is also an arithmetic progression. The only restriction out here is that fixed element must be added to each of its term. You need to identify a fixed element added in each of its term. Fixed element added in each of its term is how we identify the arithmetic progression in its own definition. Now, let's see the general form of representing the arithmetic progression. Now that we have defined what kind of a pattern makes an arithmetic progression, now next comes with the concept on how we can solve many of the problems involving arithmetic progression. Now in that case, initially I start with the general form of representing an arithmetic progression. So the general form of representation of arithmetic progression is done generally by taking in the form A. Now because the pattern says that there is a fixed element added to each of its term, let me take the fixed element as D. So I take the fixed element which is added to each of the terms as A plus D and A plus D plus D, because it is added to this, and this becomes A plus 2D plus D, is how I get the pattern. Because every time I add D to the previous term, because A plus D plus D is A plus 2D, and I get like this. So that this on further modification gives me A plus D, A plus 2D, A plus 3D, A plus 4D, and so on and so forth, is how we get the pattern. But it cannot have infinitely many terms, because if I say it is the first n terms, then it reduces to A plus n minus 1 into D. The reason being that my second term has 1D, my third term, first, second, third term has 2D, 1 less of 3, my fourth term has 3, 1 less of 4, fifth term has 4, so my nth term has n minus 1. 1 less than n. So therefore, my nth term would be a plus n minus 1 times of d, following with the pattern, is how we get this general form. This is called the general form of representing the arithmetic progression. So this is the general form of representing the arithmetic progression, where a is called the first term and d is called the common difference, because every time you take the difference, I get d. The difference of this is d, the difference of this is d, the difference of this is d, and the difference of this is d, so on and so forth. I get a common difference every time. The difference is always same. Therefore, d is called the common difference for the given arithmetic sequence, is how we identify each of them. Now, in this case, my first term is denoted generally with a1. That means the first term is a, which is a1 equal to a. Similarly, my second term of the arithmetic progression in general is denoted with a2, and a2 stands for second term. Therefore, the second term, first and second term, is a plus d. Therefore, my a2 is a plus d. And similarly, my third term, a3, will be a plus 2d. Therefore, the third term, a3, is a plus 2d. And similarly, my fourth term, a4, is a plus 3d, and so on. My n minus 1th term, denoted by a n minus 1, will be a plus n minus 2 times d, because my nth term is n minus 1d. So my n minus 1 term is n minus 2d plus a, of course, denoted by a minus 1. So finally, my last term, which is the nth term, is an equals a plus n minus 1 times d. Is how we identify the formula in general. The nth term is an equals a plus n minus 1 times d. The first term is a, the common difference is d, the nth term is this. So the general form of arithmetic progression is denoted by a plus d, a plus 2d, a plus 3d, so on and so forth till a plus n minus 1d, where a is the first term, d is the common difference, and a plus n minus 1d, denoted by an, is the nth term, is how we understand the arithmetic progression through the basic formula. Now here, the common difference d is generally the difference of the term minus its previous term, because if I wanted to get d, a plus 3d minus a plus 2d gives me d, and this minus this gives me d, or this minus this gives me d, or this minus this gives me d, which makes me understand that the common difference d is given by the formula nth term minus its previous nth term, that is a n minus 1, is how we identify the formula of d. The common difference is given as the term minus its previous term. Can also be read as term minus previous term or immediate previous term. The successive previous term is how I get the formula for the common difference d.